All right, so in this case, we have the limit as x goes to negative infinity, but the numerator goes to negative infinity. The denominator actually turns out goes to positive infinity, so we can use the same technique here. This is equal to the limit negative infinity. Divide through by the largest power of x that appears in the denominator. The question is, what do we divide by? Not x cubed. It is not the largest power of x that appears anywhere. It's the largest power of x that appears in the denominator. So ignore this. Choose the largest power of x. We need the x to the second. So everybody gets divided by x to the second. 5x to the third over x to the second plus x over x to the second, x to the second over x to the second, 4x over x to the second, minus 1 over x to the second. And now simplify like crazy. This is negative infinity. All right, x to the second denominator, x to the third numerator, this simplifies to 5x. All right. This is plus 1 over x. Here this is 1. This is 4 over x. And this is minus 1 over x squared. All right. Now, apply that property, but notice it does not apply here because this x is not in denominator. Yes, this goes to 0. These two both go to 0, but this does not. Right? So we still have a variable here. I'm going to still write this LIM because there's still some limit to be evaluated. We need to know what happens with this numerator. Well, as x goes to negative infinity, this is now substitute and simplify. 5 times negative infinity, knowing our infinity arithmetic, that's negative infinity. And so, it is possible that this limit of these types of functions, it could turn out to be positive infinity, it could turn out to be negative infinity, it could turn out to be 0, it could turn out to be any finite number. This technique is the procedure for determining that limit value. Now, there is something that some of you may have heard about before in a previous course. You will certainly learn about it in Calculus 2. It's called L'Hopital's rule. It turns out that this problem could be done with L'Hopital's rule, and so sometimes students wonder, well, why do we need to bother with this technique? There are some circumstances, and you will encounter these in Calc 2. There are some circumstances where L'Hopital's rule does not work. And in order to evaluate those kinds of limits, you must resort to this technique. So, there are some times when L'Hopital's rule does apply and it makes it easier. In that case, when you get to Calc 2, go crazy. Use L'Hopital's rule. But there are some circumstances where L'Hopital's rule is not sufficient for the task. In those scenarios, very often what you'll need to do is fall back and use this technique. In fact, when I teach this in Calc 2, I'll say, if L'Hopital's rule does not apply, then you need to use the methods you learned from Calc 1. This is what I'll be talking about, is this particular notion. Now, the last piece is this. What does this mean in terms of the graph? As x goes to negative infinity, we're saying the limit value is negative infinity. That means this. This means as you recede out the x-axis, this means you recede down the y-axis. So the further out the x-axis negative you go, the further down the y-axis negative you go. And so what this means is, way back when you drew some function and you made this little arrow, what you were indicating is this kind of behavior. Similarly, if we have limit x approaches infinity of some function, if that works out to be positive infinity, that means the further out the x-axis you go, the further up the y-axis you go. It means that. Every time you've ever drawn that in a basic algebra course, what you were doing was indicating this behavior, it's just at the time you didn't realize it. So that's the technique for evaluating these kinds of limits. It's straightforward, but you need to practice that technique.